Here we have another question from the 2010 AP Calculus exam. This one, like a previous question we've worked through, has to do with a number of different topics. So we start with a little bit of the fundamental theorem of calculus. We're going to look at our critical points, points of inflections, maximums, minimums, and later on some, again, work with derivatives, and once again those critical points. All right, as always, sharpen the axe. Read the question, make some notes, circle some important information that you may need. All right, so we have our graph. Again, making note, this is the graph of the derivative of g. The function g is defined and differentiable on this closed interval. We have this point, g of 0 equals 5. So later on when we do the first fundamental theorem, that's one that we're going to want to include in our integral. The graph of y equals g prime x, the derivative of g consists of a semicircle and 3 line segments, so they're just explaining what the graph looks like, and you can see we do have a few indicated points on our graph as well. We're going to find g of 3, g of negative 2. We want to find all the points of inflection. And finally, we're also going to work with h, a combination of g and a new function, 1/2 x squared, and find those critical points, relative maximums and minimums. Okay, so let's get started. All right, we're going to find g of 3. So when we get something like this, we're using the first fundamental theorem of calculus. Now, the first fundamental theorem of calculus, remember, the integral of some function is the antiderivative evaluated at the top minus the bottom. So I want g of 3. I want to know g of this point right here. Okay, well, I do know g of 0. So I'm going to set up this integral from here to here. So let's take the integral from 0 to 3, and you can see we're using one of those terms that we know, g of 0, of g prime x dx. And the first fundamental theorem says that's going to give me g, the antiderivative of g prime, is going to get me back to g evaluated at 3 minus g evaluated at 0, top minus bottom. All right, so this first part here is just the area under our curve. Let's spell that right. That's just the area in here. And this little piece here. And then g of 3, that's what we're looking for. And this one we know from our description, we know that is 5. All right, so let's go ahead and see if we can calculate some of these things. So I'm going to find the area of this little circle part right here. Well, that area is actually a quarter of our circle. And our circle area, pi r, the radius is 2 squared. And when we have 2 squared and pi, this area here is just going to be pi. Now I'm not quite done because I need this little bit here. If I'm going from 0 to 3, I need this little bit. So I need the area of that little triangle, which is going to be base times the height. And we got the 3 right off the information from the graph, divided by 2. So we look at that, that's 3 over 2. So this total area here, let me go back and erase this. The total area then becomes pi plus 3/2. All right, and that is g of 3 minus 5. Okay, let's slide this up. So now we're just working with this particular algebraic expression right here. I'm going to bring my negative 5 over to the other side. So that's actually, we're going to add 5 here, and we're going to add 5 over here. So when we're done, we're going to get g of 3. And we now have pi plus, this is 3 halves plus 5, so this is like 10 halves. So that will give me plus 13 halves. And there's g of 3. Okay, let's keep going because we also want to find g of negative 2. G of negative 2. So I'm going to need my picture again, so I'm just going to one more time. Okay, so here's our picture back. Now we want g of negative 2, so we want this part over here. Well, I'm going to set up my integral, and now I'm going to go from negative 2 to 0. Again, we're trying to use one of the pieces that we know for sure here. And of g prime x dx. And that is going to give me top minus bottom. That's negative 2. All right, so again, this first part here is just my area under the curve. I want the area of all of this from, oops, not all of that, sorry. We are going just this first part, from negative 2 to 0. G of 0 we know from our information, that is 5, and this is what we're going to try and find. All right, let's go ahead, find my area again. Well, we notice we've actually done this before. That area is a quarter of my circle, so that area is just pi 5 minus g of negative 2. All right, now I want to find g of 2. I'm going to, just slide this up. So we're going to find g of 2. I'm going to actually move my g over and move the pi over here. So we get g of negative 2 is 5 minus pi. There's our first two. Okay, let's keep going. All right, for part B, we want to find all the points of inflection for the graph of y equals g of x on the interval negative 7 to 5. So we've done this a few times. You may have some shortcuts already. You're looking for really when the derivative is going from positive to negative or negative to positive, increasing and decreasing. I like to still just set up my 3 windows. So I'm going to go back and look at g, g prime, and g double prime. Let's put on some of our interesting points here. So I'm going to put on my endpoints, negative 7. Then again here something happens at negative 2. I'm going to put this maximum, relative maximum there at 0. Here's another 0 happening here at 2. Need to extend this a little bit. Let's go this maximum here at 3, and we don't really know what's happening there. Kind of looks like maybe 4.5. We can put it on there. And my other endpoint was 5. So what we're going to do is figure out what is happening to g prime and then relate it to its derivative and all the way back to the original. So from negative 7 to negative 2, my derivative is increasing. That means g double prime would have to be positive. We go all the way back, g is concave up. Between negative 2 and 0, we're still increasing. So its derivative is positive. Going all the way back, g is still concave up. From 0 to 2 now, we're decreasing. That means its derivative, g double prime, would have to be negative. And if we go all the way back, g would be concave down. So now we have a switch between concave up and concave down. There is our first point of inflection. From 2 to 3, we're increasing. Its derivative is positive, and g is back to concave up. So there's another switch from concave up to concave down, or concave down to concave up. And finally, after 3, we're going down, and in fact, we go down all the way. We're always going down here, so it didn't matter what that was. We're going down. That means its derivative is always negative, and we are concave down. So once again, we see this little piece right here. We've gone from concave up to concave down, so we also have a point of inflection at 3. Okay, we have one more piece to this question. We have a new function h. H is defined as g of x minus 1/2 x squared, right in here. And we want to find, again, those critical points. So where are we going to get maximums or minimums? And then we're going to label them as either a maximum or a minimum and explain how we did that. Okay, so we know maximums and minimums occur when the derivative is equal to 0. So I'm going to find the derivative of h. So I'm going to take the derivative of this part, g prime x, and the derivative of this second piece. So if I bring the 2 down in front, the 2 and the 1/2 kind of cancel each other, and I get negative x. So there's my derivative of h of x. We want that to equal 0. Okay. Well, if we look, let's do a little rearranging, move that over. G prime of x has to equal x. Well, this is g prime of x. These are our numbers for g prime of x. So we're basically saying, when does x equal y? So on our graph, we're looking at anything that falls along that line right there. So we can see we're going to get 1 point right here, and we get another one that's nice. We can read that one right off the graph there. So in fact, 1 point we already have, and that is 3. Let's figure out what this point is. Okay, I'm just going to slide this up a little bit. So, actually I'm not going to slide it up because I want to refer to this picture here first of all. Remember, we got a semicircle here. So using my information on circles, we know that's x squared plus y squared equals r squared. So if I do a little rearranging, my radius is 2, so that's going to be a 4. I'm going to move my x squared over, and that becomes negative x squared. Now that is y squared, so I'm going to take the square root of that whole thing. So now what I have is g prime x is, at this point, 4 minus x squared, and we want that to equal x. Okay, now I'm running out of space. I'm going to slide this up, solve this little piece right here. So let's square both sides, and I get 4 minus x squared equals x squared. Let's move that over. 4 equals 2x squared. Divide off that 2. 2 is equal to x squared. So x is equal to the root of 2. So if I go all the way back now, let's get back here. That means this point up here is the root 2. Okay, well what we have to do is we have to then classify them as a maximum or a minimum. So I'm going to draw my little line here. That's h prime, and that's h, and we're going to test root 2, and we're going to test 3. So there's our 3 windows. Let's figure out if they're maximums or minimums. So I need something in this interval here less than root 2. So 0 works nice. So remember, this was h prime right back here, g prime minus x. So h prime of 0, well, g prime of 0 is actually 2 minus 0. That is 2, that is positive, and we are increasing. We need something in this interval right here. So again, 2 works, and 2 is nice because we know what that is, right? 2 is in the interval between root 2 and 3, so let's go h prime of 2. Well, g prime of 2 is 0 minus 2, so that is going to be negative, and we're going down. So root 2 is a maximum. Let's try something else in this interval here. Well, 5 works, so let's do h prime of 5. G prime of 5 is negative 1 minus 5. Well, that's negative, and we're still going down, so 3 is actually neither a maximum or a minimum. Okay, So this is our critical points. Now let's just slide up and make sure we make that final statement. We get relative max at x equal to root 2 and sorry, not that, neither max or min at x equal to 3. And there we go.